one of the fastest Nobel Prize awarded within 5 years, I think, since the first paper come out. Within 5 years, this guy got the Nobel Prize because the Nobel Committee see the impact of such a tool for science. And Nobel is all about impact. It's all about what kind of invention that you have impact on the way the world works. And this tool, in fact, has significant impact.
So basically the tunneling is just because the wave functions overlap, or is it because of the applied voltage?
You have wave function overlap, and then you have to put a bias on it to get the electron to move in the direction you want. If you don't have, if your wave function is not close enough, even applying the voltage, you will not move with that. Okay, so that's a good point. You first have to have the wave function overlap first, and then in order to move the electron in the direction you want, because you have different source of electron, then you need a bias. Okay, so the bias comes second. The physics have to work first. The bias is just engineering, is what I would say. Just engineering how you select the electron that you want to sample. And every university almost have one. I'm pretty sure all the decent universities will have one. At WaLab we have one, and a really nice microscope. My student been working on this, and people interested can come and take a look and talk to my student Abhishek, and he can show you. He actually can make very good tip, atomic sharp tip, to be used in the microscope, and you can get very good image. I'll show you some of the images that we collected, such as this one, for example. This is a atomically sharp image collected by Abhishek, my student. So this is the so-called 7x7 image. I'll come back to this. I want to introduce a little bit about the 7x7, and then we come back to this picture. But so mechanical tunneling phenomena. So the magnitude of the tunneling. So this is the physics. This is it. So it's very simple physics. We know about it from quantum mechanics. So the intensity proportional to the wave function density, right? Wave function is not a physical phenomenon. It's not a measurable quantity in quantum mechanics, but the density is, right? Density is the probability of the wave functions, okay? So according to the postulates in quantum mechanics, we know the wave function squared can be measured with the probability of the wave functions. So you have the surface atom, you have the tip atom, right? And the connection between the two is an exponential factor, and this S here is the spacing between the two atoms that you have. Okay, and so the inverse length of the wavelength of the wave function is K. Is given by this constant times the work function, right? So this is the work function, and so a typical work function is about 4 eV, and 4 eV will give you K roughly 1 angstrom, inverse angstrom, something like that. Okay, so now if you can somehow measure these times, so the idea is that, so this is the overlap, this is the current. If you can somehow measure this really tiny amount of current, right, due to charge transfer between the surface and the tip, then how do you move charge transfer? You have to apply a small bias to move the electron. Then we can obtain the so-called local density state. So you can treat this whole thing, right? If you can somehow position it, you can treat the second part of this thing as a delta function, right? So you move it, you move your tip just on top of the surface atom. So in this case, your electron density is just proportional to the wave function density, right? Wave function density, and that's it. Notice I say this is wave function, electron wave function density, not the nuclear position. Okay, so you have to be careful about this. Why is this important? Well, because it doesn't really, a common mistake that people found is that STM is not really a probe that probe the nuclear position. It probes the position of the electron density. So for example, if you have two hydrogen atoms, right? If you're probing the sigma bond, you get the position of hydrogen atom nuclei wrong, because the sigma bond, of course, the electron density is in between, right? In between the two nuclei. That's where your sigma bond is in terms of the H2 molecule, right? So it cannot tell you the location of nuclei of the H2 molecule, but it can tell you the location of where the electrons are concentrated, if you like, for each orbitals. Okay, so very important point to recognize. Unlike if you like, lead or fine structure and things like that, they are a nuclear-based type. So it tells you electron density state, right? So the key point, electron density, because is the current density proportional to the wave function density. So we can do a couple of things. We can keep the current constant. So this is where the feedback electronic is important. You can set a certain current that you want to measure, and you try to keep this constant as you apply voltage to your piezo and scan your tip. You move your tip X and Y direction and so forth. And at the same time, when you are trying to keep this current constant, how do you do that? Well, you can move your tip up and down, right? So you have some sort of profiler, right? Some sort of profiler. You're moving it around so that you're keeping this current density constant, and you got the topography of the surface. Okay. So this is the point I'm talking about when I'm talking about two hydrogen atoms, right? You code the electron density. If you're talking about sigma bond, of course the electron sharing of this sigma bond, you are probing the middle. So you see one dot instead of two dots corresponding nuclei. That's what STM tells you, right? So don't get misled by the ability of the technique. So this is a topography. Basically, you're measuring S here, the up and down separation distance. So here you have, in order to get the electron to move, you must encourage it by applying a bias potential. So usually, you put the bias on the sample. You apply a small voltage of the order of between half a volt to 2.5 volts, something like that. You don't apply so much voltage. It's a very low voltage tool. No more than 3 volts for sure. And it will move you bias the sample in two different ways. You can either put a negative bias, right? You can put a negative bias on the sample, meaning your surface. So you put a negative bias on this. This is my sample here. And what happens? If you put a negative bias, then tunneling will go from the occupied state, right, of the negative bias. Basically, you're pushing your electron out. If you have negative bias, you're pushing your negative electron out of your sample into the empty state of the tip, right? Into the empty state. So they are unoccupied state, unoccupied orbital. Think of it, unoccupied of the tip. And a tip. What is this tip atom? Tip atom is usually made of tungsten or palladium, depending on how you want to make it. The tip that Avishek makes is made out of tungsten. You can do it in the lab, quite not so difficult task. So tungsten is an atom, so it also get its electronic energy level. So you can apply a negative, push the electron out from the filled state, occupied state, where you must have electron already in your sample atoms, surface atoms, and push it out onto the tip atom, empty state of tip atom. If the sample is positive, bias is positive, what happens? Then the reverse will occur. So you are now sucking electron from the tip atom, right, into the surface, So you apply positive here, so you are sucking electron from the filled state of the tip atom into the empty state of the surface. Okay, so you